suppose that G is a group, and H is a subgroup. H is a subset of G. Also, it must follow that X inverse is in H. Three things to do. Now there is this theorem that says you can reduce this to two things, so it's shorter. And one of those things is almost always trivial. So instead of doing these three things, you can do these two things. Check the subset is not empty, which is generally obvious because you can exhibit an element. And show the following. If X and Y are in H, it must follow that X, Y inverse. Now Y inverse is a unique element of G. So these are two elements. That's definitely in H. This is an element of G at the moment. So because everything's going on inside G, we can form this product and it will be an element of G. But what we want is that it's actually in the subset. So this takes almost no work, and all the checking here is reduced to checking one thing, this fact. And we proved in lectures that if these things are true, then these are true, but equivalently, if these things are true, not equivalently, but it's also the case that if these are true, then these are true. I could go over the proof if you want, but that's the philosophy. So the person who is concerned about this, are you now happy about that? Are you here? Possibly not. Okay. Never mind, the rest of you got the benefit. Asked to talk about cyclic groups and Cayley's theorem at my 12:15 session. I think we talked about cyclic groups yesterday. We didn't talk about Cayley's theorem. Shall I talk about that for a moment? Cayley. Okay, so Cayley's theorem is about saying, it's about this idea. I've got a group. It's not necessarily a group of permutations. It could be a group of anything, just elements with a combination law. I dream, my big wish in life is that it should be a permutation group. Okay, Cayley's theorem says you can arrange that. So G, any group, introduce a set S, which is equal to G. Right. Let G act on S by multiply a group element by an element of the set, and it's just ordinary group multiplication. And then, when you do that, what happens? So, let's have this turns G into a permutation group. So, rather than do it abstractly, I propose to do it concretely. Okay, so let's take G is the group of symmetries of an equilateral triangle. Okay, so the elements are identity, rotation through 2 pi by 3, rotation through minus 2 pi by 3, the inverse, so let's call this alpha and this alpha inverse. The product of these two things is the identity. And then you could turn it over about these axes of symmetry. So let's call beta delta, beta gamma delta. Beta gamma delta. And these are reflections in the axes of symmetry shown. Blah, blah, and blah. Okay, so one way you could term this this group, the group G is going to have size 6. You can take the equilateral triangle out, and you can either rotate it or you can turn it over. And there are 3 ways of rotating it, and there are 3 ways of turning it over, and that's it. So the size of the group is 6. One way to turn it into a permutation group is to label the vertices 1, 2, and 3, and associate to each group element the permutation of the vertices. But somehow we're using the fact that this is our group is a collection of symmetries of a geometrical object which we can label. But Cayley's theorem works in complete generality. You don't need to have an underlying geometric object. So what you do is you let omega, well, you let S be the set id alpha, alpha inverse, beta, gamma, delta, and you associate to alpha, for example, left multiplication by alpha. So let's see what this does. So lambda alpha sends the identity to alpha. It sends alpha to alpha squared. Alpha squared is a rotation. This is going to be the other rotation is going to be alpha inverse. Alpha inverse multiplied by alpha is going to be the identity. And then we just got to see what happens to beta, gamma, and delta. Right, so now we have to do a little bit of work. So if we first do beta and then alpha, beta fixes beta and exchanges these two points. So if I first do beta and then do alpha, what will happen? Well, beta is fixed and then it goes to gamma. So beta gets sent to gamma. Right. What happens to gamma on the other hand? Well, what does beta do to gamma? It sends it to delta, and then alpha rotates it to beta. So the effect of this product is to do this exchange. It means that what is going to happen to delta delta is going to have to be fixed. But this is the map that fixes delta and exchanges those two things. It's called delta. Right. Well, maybe we can do a shortcut and do no more work. So what's going to go here is gamma and beta and gamma, one way around. But gamma does not map to gamma because alpha gamma is not gamma. If it were, then you could cancel the gammas and learn that alpha is the identity, which it isn't. So it can't be that alpha gamma is gamma, so the only possibility is that alpha gamma is beta. And then the only thing that remains here, given that we're dealing with a permutation, is gamma. Now if you want actual concrete numbers, you could label these 6 group elements, 1, 2, 3, 4, 5, and 6, and left multiplication by alpha would then be a particular permutation of 1, 2, 3, 4, 5, or 6, and you could write it out using cycles. Okay, and you could do the same for every group element. I'd say the main use of this is that there are a variety of computer algebra packages that enable you to calculate with groups, and the most famous one is called GAP. Stands for Groups, Algorithms and Programming, and it can handle all sorts of groups represented in all sorts of ways. It can handle groups viewed as collections of matrices, or it can handle groups viewed as collections of permutations, and it's got other formats as well that I don't want to raise today. Cayley's theorem says if you really want to, you can make any group into a permutation group, which can be very useful. So, in fact, the algorithms for doing group theory computations with permutations are really very efficient and very fast. So it's very handy to be able to view a group as a collection of permutations. Sometimes it's not possible because the group's just too big. So supposing, for example, you're dealing with a finite group that consists of 10 by 10 matrices, 10 by 10 invertible matrices with elements in the field with 11 elements. Well, if you write down a random matrix, most of the time its determinant is not zero. A random square matrix, usually its determinant is not zero, so usually it's invertible. So for a rough estimation of how big that group is, then a 10 by 10 matrix contains 100 entries, right? And then if you've got a choice of 11 entries for each entry, how many matrices could you write down? Answer 11 to the power 1,000. Because you've got 11 choices in each of 1,000 positions. Now, I'll say that the group is not quite this big because some matrices have determinant zero. But we don't have machines which can store this set this big. So you can't, there's no way to represent that group of matrices as a collection of permutations in a useful fashion. So you have to think of it as a group of matrices, because storing a group of matrices, it just contains 100 pieces of information, each of which is something between 0 and 10. This is a much more compact representation than a group of permutations, but the algorithms for manipulating matrices are far less efficient than the algorithms for manipulating permutations. It's life. Okay, have you got any specific questions, please? I also have a multiplication. And the multiplication for us has got to be associative, and this is not true. And multiplication distributes over addition. So A times B plus C is the same as AB plus AC, and the same on the right, but you don't have to say that because you've got a commutative law and you can deduce it. Right. Yes, and again, this isn't universal, but for us, there exists one in we're in a ring with R. There exists one in R such that 1 times A is equal to A is equal to A times 1 for all A in the ring. Okay, so that's what our beasts are. These are commutative rings with 1, which I'm just calling a ring. Now, we can look at we can focus upon special attributes that these things might have. And there are a vast number of different types of ring, but for the purposes of this course, we focused upon 3, or perhaps 4. Okay, so the most special are fields, and then every field is automatically an integral domain, and every integral domain is automatically a ring. So, how do you qualify for these the special status? Well, to be an integral domain, informally, you've got to be like the integers. So, you need, firstly, that 1 and 0 are not the same thing. Secondly, that if A and B are in the ring, and AB equals 0, then the only way that can happen is that if either A is 0 or B equals 0. These are properties which are clearly enjoyed by the integers. From these properties, you can deduce various things. So, in an integral domain, you get this. If x, y, z are in the ring, and xy equals xz, and x is not 0, then it follows that y equals z. So you can do some cancelling.
Can you read the page up, please?
Oh, yeah. Very good. Thank you. So I'll say it again. In one of these integral domains, a ring which is like the integers, if you've got x, y, and z, and it happens that xy equals xz, and it so happens that x is not 0, then you can cancel. It follows from this stuff up here by a little algebraic argument. This is a nice property from the point of view of constructions, because there's a theorem that says if R is an integral domain, then polynomials with coefficients in R, integral domain, that's going to be an integral domain. this is going to be polynomials with polynomials in Y with coefficients in this ring, which you can think of as being polynomials in two commuting variables with coefficients in R. And by extension, by induction argument, polynomials with coefficients in an integral domain in any finite number of commuting variables is going to be an integral domain. So you could build up. Okay. Now a field is a very special type of integral domain. It has the property that, once again, you insist that 1 and 0 have to be different. Secondly, you insist that if A is in the ring and A is not 0, then there exists B in the ring such that AB is equal to 1. So every element has a multiplicative inverse. Now, from these conditions, you can deduce these. Well, obviously, 1 is still not equal to 0, but let's deduce this second condition. So we suppose that A and B are in the ring and AB is 0. If I've got I'm now going to assume A and B are not 0 for contradiction. So assume neither is 0 for contradiction. Well, if neither is 0, then A is not 0, so it's got an inverse. So let's let A dashed is the inverse, multiplicative inverse of A, multiply by it. Well, A dashed A is going to be 1, and we proved in lectures that if you multiply in a ring, if you multiply by 0, you get 0, and you deduce that B is 0. So if A is not 0, then B is. Similarly, if B is not 0, then A is. Which is exactly what you want for this to hold. So fields are necessarily integral domains. The common letter to describe a field is K, because the comes from the German Korken, meaning a body. Okay, sometimes small k, sometimes big K. If you form polynomials with coefficients in a field, then it's not necessarily, it isn't a field, because, for example, x has no multiplicative inverse. You can't multiply x by any polynomial to make it 1. But K, since K is a field, it is an integral domain, and so this will be an integral domain. So you can multiply together non-zero polynomials with coefficients in K, a field, then you get a non-zero polynomial with coefficients in K. But an arbitrary ring does not have these special properties. So you don't have to look very far. So, for example, what I could do is to consider R cross R, ordered pairs of real numbers, with operations coordinate-wise. So alpha beta plus gamma delta is alpha plus gamma, beta plus delta. And multiplication, alpha beta times gamma delta is going to be alpha gamma beta delta. Well, it's a completely routine matter to check that the ring axioms are satisfied. you're going to have a multiplicative identity, which is going to be 1, comma 1. So it's going to be the 1 of this ring here. Let's give this ring a name. Let's call it B for bath. It's the bath ring. And the multiplicative identity of the bath ring is 1, comma 1. But this is not an integral domain, and so not a field, because 1, 0 times 0, 1 is 0, 0. So you can multiply together non-zero elements of the ring B, and you can get 0. So it is neither, it's not an integral domain, and therefore definitely not a field. Is that better? Yeah. Good. Any more questions, please? You can stop if you want, but this is your last chance. Unless you come along at 12:15. Are there revision sessions in the other lectures or not? In the other courses? Yeah. No?
Could you give us an outline of Bezo's theorem for polynomial rings?
Well, it's the same. It is the same as. So, K is a field. I look at two polynomials with coefficients in K, and I assume that F and G are not both 0. And first off, Euclid's algorithm works. So I can perform Euclid's algorithm. So let's assume without sort of generality that G is not 0. Then I write F is equal to a polynomial times G plus a remainder where Q and R are polynomials. And the degree of R is less than the degree of the thing that you're dividing by. You're all happy to have to divide one polynomial by another, possibly failing with a small remainder. You all done that? Yeah. Okay, so you follow now you know how to divide. You can do Euclid's algorithm. You can get an output. I'll call it H, a polynomial in K, and then H is the inverted commas GCD of F and G. There's some flexibility here, just as if you talked about the greatest common divisor of 6 and 9, the answer would be 3, but in many senses, -3 is almost as good. -3 is a common divisor of 6 and 9, and any common divisor of 6 and 9 divides -3. The only thing that's wrong with -3 is that it's negative, and so we decide not to use it, but that's a kind of life choice. With polynomials, you have more flexibility. The leading coefficient, okay, if you've got a candidate for the GCD of F and G, if you multiply it by any non-zero constant from a field, you've got another polynomial which is, in some sense, just as good. So that means that you have the option of multiplying through by the appropriate constant to make the largest power of x have coefficient 1. So you can choose to make h Okay, now if you unwrap Euclid's algorithm in just the way that you do for the integers, what you will discover is that there exist polynomials, lambda and mu, with coefficients in k, such that the GCD is equal to the polynomial lambda times the polynomial f plus the polynomial mu times the polynomial g. And there is absolutely no difference from the process that you would do when you're working with integers. Exactly the same. Is that okay? Is that what you wanted? Yeah. So much better to do it on a computer algebra system than actually perform it by hand, because it's fiddly. But it's, of course, sometimes you don't actually have to find lambda and mu. Sometimes their existence is enough for you to do mathematics with. So that's fine. Any more questions, please? Yes, please.
When you're checking if a group is a subgroup,
Yeah.
and you have to use the two checks,
Yeah.
how do you reference that in the exam? So
So what I do is to simply perform the two checks.
okay.
One, observe that the set is not empty because, insert reason, probably because you can write down an element of it. Okay. 2, choose any x and y in H, and then do a proof that xy inverse is in H. Perfectly enough. The marking is extremely relaxed. We're not looking for hyper. It's not going to be hyper picky, right? If you show willing, the marks will flow. Any more questions, please? Yes.
If you have a group with like 5 elements, how do you find how many elements have order 2 within that group?
Okay. So in that case, what I would do is to say, I've got a group of order 5. So Lagrange's theorem tells me that the size of any subgroup must be a divisor of 5. Right? And then I would say, well, the order of an element is defined in 2 different ways, but one of the ways which is defined is that it is the size of the subgroup consisting of the powers of that element. So if you've got an element of order 2, it and its square, which is the identity, will form a subgroup of size 2. And 2 doesn't divide 5, so the answer is 0. Right. Now, so that was easy. But if, for example, there's an old exam question, which I discussed with one of the groups yesterday, which was, I think, looking inside S6 and asks how many elements have order 3. Have you done that particular part of paper?
I've seen it in computer
Yeah.
version, yeah.
Okay, so shall we do it now? Okay, so elements of order 3 inside S6 have got 2 choices in life. Either they're going to be a 3 cycle, or they're going to be a product of 3 cycles with nothing in common. So the word for that, disjoint. That's to say, the elements listed in this cycle are different from the elements listed in that cycle. So I'm going to, because the thing is that all cycles involved are going to have to be divisors of 3 if your element's going to have order 3. Is that okay? Yeah. So they could all be 1 cycles. In that case, you're dealing with the identity element of the group. It doesn't have order 3, it has order 1. So, we're looking for these. So this is the easier type. You can choose the three things which go in here from amongst the 6 possible numbers in 6 choose 3 ways. Now, if you've got 3 of them, perhaps 1, 2 and 3, these permutations are all the same permutation. They're different ways of writing the same thing. 1 goes to 2, goes to 3, goes to 1, goes to 2, goes to 3, goes to 1, goes to... Okay. So if you've got a 3 cycle, you can always take the smallest entry and put it at the front. So I choose the 3 things which are going to go there in 6 choose 3 ways. I put the smallest at the front, and then the other 2 can go in 2 ways round. Right, so that's going to be the answer for how many 3 cycles there are. 6 choose 3 is 20, so that's going to be 40. Now, the next one's slightly fiddlier. So let's look at this first 3 cycle. I could choose the 3 elements to go there in 6 choose 3 ways, and then by the same argument I got before, those three numbers will give rise to 6 choose 3 times 2 permutations. Now I've got no more choices, because I've got no choice about what the numbers are that go here. They're the numbers which don't go there. So that's forced. I can write the smaller one at the beginning, the smallest of the 3 numbers I'll put there, and the other 2 can go one way round or the other. So that gives me another factor of 2 there. But now I have to be very careful, because I've actually created, or I've counted, every possible permutation twice, because for example, the permutation 1 goes to 2, goes to 3, goes to 1 in one cycle, and 4 goes to 5, goes to 6, is the same permutation as 4 goes to 5, goes to 6, followed by 1 goes to 2, goes to 3. So everything's been counted twice. So I have to divide by 2. Once again, it turns out then that there are 40 elements of order 3, which are the products of 2 disjoint 3 cycles. So the final answer is 80, being 40 plus 40. Okay. What geometrical representation?
Is the adjugate matrix.
I don't know one. Okay, it's just the adjugate matrix. So, well, hang on. So, if you've got A, it's a square matrix. Then the adjugate matrix, I don't know if that's the notation for it that you're using, is the matrix of the same size, but you put the cofactors in instead of the original entries. And so, A adj times A will be det A times the n by n identity matrix. So, A adj will be equal to the inverse of A times the determinant of A. So up to a multiplicative factor of the determinant of A, the fiddle factor, the adjugate matrix turns out to be the inverse. The inverse matrix undoes the work of example, we're dealing with 2 by 2 matrices, then what does a matrix do? If you apply it to 2 elements of the plane, you're looking for a geometric representation, and I'm struggling towards you. Okay, so the matrix is acting on the plane, and what happens is that what we normally do is you consider what happens to 1, 0 and 0, 1, and they end up somewhere else, perhaps here and here, and what's happening is that this little box is being transformed into that parallelogram. And there's some kind of shearing and rotating process going on, some fairly kind transformation of the plane. Okay, something very pleasant going on, and the inverse matrix undoes that. And okay, it's not quite the inverse matrix. There's this scale factor of the determinant that just multiplies everything by a constant, which is inflation from the origin. And if the determinant is negative, you end up going the other way, out the back of the origin. You go back through the origin, go the other way. Okay, so yes, but this is all happening because I have a geometric representation of the real numbers, and implicitly I'm assuming that I'm dealing with real matrices. So you can picture it. But if it's what's going on, if it's an n by n matrix, and the entries come from the reals, okay, it's some natural generalization. If the entries are complex numbers, it's geometry, but it's less easy to see what's going on. And if they come from a finite field or something, then, well, there are these things called finite geometries and so on. So the geometry can be made to be there. Yeah. Please.
In the symmetric group on n letters,
Yes.
why are two elements of the same cycle shape conjugates?
Okay. So what I'm going to, you conjugate the other way around, don't you? You conjugate like that. Okay. So let's take let's just look at it as a concrete example. There's a group element, and I'm conjugating it. So what do I get? I just swap those two around in order to get the inverse. And let's see what happens. What happens to 1? 1 is unmoved, then it's sent to 2, and then it's sent to 4. So 1 gets sent to 4. Right. What happens to 4? 4 gets sent to 2, and then it gets sent to 3, and then it's unmoved. What happens to 3? Okay, 3 is unmoved, it gets sent to 1, and then it's unmoved. 2 is unmoved, and 5 is unmoved, and that's it. So what's happened is that 1, 2, 3 has been replaced by 1, 4. So 1 has been fixed, 2 has been sent to 4, and 3 has been 3 has been fixed. So what's happened is that it is as if I had taken these 3 elements and I had applied this to them. So 1 is left alone by this, it becomes 1. 2 is sent to 4 by this permutation. Goes there, and 3 is left alone by this permutation, so it stays there. So the effect of conjugation is simply to take the entries of this cycle and replace them according to the rule given by the conjugating element. So you run away and you check that that is not just an accident for 1, 2 and 3, it works for any cycle. And then once it works for any cycle, it will work for products of cycles. That's a straightforward algebraic consequence. So, that means that tells you more than you asked. If you conjugate an element, what will happen is that it will have the same shape and the entries of the conjugated element can be read off by looking at the original elements and acting upon them by this conjugating element. So it tells you also what elements should go here. So, for example, if I conjugate 2, 4, 5, and now do 1, 2, 3, 4, 5. Okay, so it's slightly more complicated. I've got this extra bit in here. Okay, well that's 2, 4, 5 times 1, 2, 3 times 2, 4, 5 inverse times 2, 4, 5 times 4, 5 times 2, 4, 5 inverse. Now what I've done is I've inserted the identity map in the middle, written like this. But when I've done that, you've got a conjugation times a conjugation. And you know how to do each of those two things. You simply substitute it, you take this cycle and you replace it according to this rule. Okay, 1 maps to 1, 2 maps to 4, 3 maps to 3. I do the same thing here. I take 4, 5 and I replace the 4, 5 by 5 because 4 maps to 5 and 5 on the other hand maps to 2. I've done it. You probably don't like that because it's the wrong way round, but you can just tidy up. So I've done the conjugation. And it's the same shape and the entries are as specified. Okay. Any more questions, please? Okay. So I see you at 12:15, or best of luck in the exam. Or indeed both. It really won't be so bad.